Testing, 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 testing. All right, audio working. Stream ready. Ready to go. Welcome to another Hoopo stream. We got a paper today to finish off the week. This is a paper from Google. This is the address of Google at Mountain View, California, which is in San Francisco in the Bay Area. We got speed is all you need, which is a reference to the paper attention is all you need, which is the paper that introduced transformers, which of course is the famous architecture improvement that people credit for the advance in AI. 21st of April, so a little bit of an older paper now, a little bit over a week, but yeah, a little bit different from what we were looking before. This is going to be about GPU inference and how they sped it up. So assuming they did some tricky stuff, perhaps it's even stuff that only works on TPUs, right? TPUs are Google's hardware that they use to train. So you got TPUs. Ever seen a TPU? None of these are TPUs. This is a TPU. This is a TPU 4 pod, so you got 4 TPUs here. And then you basically have these large server racks where you have racks and racks of these pods. I think they're on TPU v5. Is that the next one? The one that they're on? TPU v5? Not PPU. How are TPU different from GPU? TPU and GPUs are basically the same thing. So TPU stands for Tensor Processing Unit. GPU stands for Graphics Processing Unit. So GPUs were originally designed for video games, and then it just so happened that they worked well for deep learning, and then they became used for deep learnings. But pause AI, yes or no? But then the TPU was made specifically for deep learning. So I think the latest one, the TPU v5, is not just specifically for deep learning, but it's also specifically for transformers. So I guess TPU v5 is the one they're trying to make. I guess TPU v4 is the one that they have available. So v5 isn't necessarily available yet. But largely they're the same thing. They're computers that are very good at calculating large batches of simple arithmetic rather than very, very fast single kind of thing. So is it faster, or why would one choose TPU? The speed doesn't necessarily matter. I don't think the speed of a single TPU compared to the speed of a single NVIDIA card is important, because 10 TPUs are always going to be better than 1 GPU, and 10 GPUs are always going to be better than 1 TPU. So it's not like you're gaining something by using one over the other. It just comes down to how many of each one do you have access to. So why would you use a TPU instead of a GPU? Well, if you open up a Colab, right, these Colab notebooks, right, you can connect it to a TPU, right? So Google doesn't have NVIDIA GPUs for you to use. If you want to have a Colab that uses a GPU, they only let you use TPUs. So the reason you would use a TPU is because you're writing something in TensorFlow, or you're using Google Cloud, or you're using a Colab notebook that has free TPUs. The reason you would use a GPU is because you're doing something on your local computer, which has an NVIDIA GPU, or you're using the Amazon cloud, which has NVIDIA GPUs. So there isn't necessarily a huge advantage to pick one over the other. It's just whichever one you have available to, and that's about it. All right, let's get to it here. Abstract. The rapid development and application of foundation models. Foundation models here just basically means very large models trained on a very large amount of data. Have revolutionized the field. Large diffusion models. So diffusion models are the image generation models that power Stable Diffusion and DALL-E. Have gained significant attention for their ability to generate photorealistic images. On-device deployment, so here I guess they mean cell phones probably, provides benefits such as lower server cost, offline functionality, and improved user privacy. So what do they mean by here? So lower server cost. If you use, for example, ChatGPT, this isn't running on your local computer. This is running on Azure Microsoft Cloud. So you're sending a request. There's some GPU in some giant data center somewhere in, I don't know where Microsoft has their data centers, but some GPU in this giant server room processes your request and then sends it back to you over the internet. So if people can just run these models on their cell phones, then you don't need to have these data centers, and it's going to lower the server cost. Offline functionality means that you don't need to be sending stuff over the internet and then send it back. And then improved user privacy is because you don't actually, let's say you take a picture and then that picture can be basically processed on your device. And I guess maybe the picture's the wrong example, but maybe you're using Stable Diffusion on your cell phone and you generate it on your cell phone. Google's never going to know what you generated, right? No one's ever going to have to know what you generated. You could generate it with the internet off. So some people like this idea of edge compute as a way to get better user privacy. Large diffusion models have over 1 billion parameters and pose challenges due to restricted computational and memory resources on devices. Yeah, it's still very hard to run machine learning on cell phones. There have been some stuff. So MobileNet is very popular. So most deep learning frameworks have a version of this, but MobileNet is a very small computer vision model that is designed to run on cell phones. And yeah, these have been popular for quite some time now. We present a series of implementation optimizations for large diffusion models that achieve the fastest reported inference latency to date. Okay. Under 12 seconds for Stable Diffusion 1.4 without int8 quantization for a 512 by 512 image with 20 iterations. Okay. A lot of different numbers here that they just threw at you, but basically what this means is that the inference is 12 seconds, so the time from you typing in the text and then hitting enter to getting the final image out of Stable Diffusion is 12 seconds. Stable Diffusion 1.4 refers to version 1.4, which was the version that they open sourced at the very beginning, Stability AI. They're now at version 2 point something, but 1.4 has kind of become the benchmark, I guess. int8 quantization. Quantization is the process of taking a machine learning model and then reducing the precision on the data types for these parameters. And then by doing that, you can basically store a bigger model in a smaller amount of memory. 512 by 512 is the size of the image, and 20 iterations is the number of diffusion steps. So diffusion models, you have to basically perform a bunch of noise removal steps in a row. And for example, a GAN, you don't have to do that. In a generative adversarial network, you can just perform inference in one step. But with these diffusion models, you need to perform inference many times in a row because you're iteratively removing. On GPU-equipped mobile devices, so currently there's mobile devices that have little tiny GPUs in them. I think the later Pixel phones have little tiny GPUs on them, but I'm not super well versed on hardware specs for phones, to be honest. These enhancements broaden the applicability of generative AI and improve the overall experience across a wide range of devices. You know what? You know who might know about this? GPT. What is the memory available in phones for this memory available in modern smartphones? 12 gigabytes. What? What phone has 12 gigabytes of GPU memory? That sounds absolutely insane. What phone has 12 gigabytes of GPU memory? I can see 2 gigabytes. I can't see 12 gigabytes. Yeah, okay, so makes a mistake. So there is no phone that has 12 gigabytes of dedicated GPU memory, but it might have 12 gigabytes of RAM, which is just normal memory, random access memory. That's the memory that your CPU uses, basically. So the Samsung Galaxy S20 Ultra has 12 gigabytes of RAM. Okay, but 2 gigabytes is pretty small, right? I think we were looking at the Dino 2 model. This is a foundational computer vision model that we were looking at earlier this week. And the VIT S14, which is the smallest one, when we actually look at the size of this, so let's open, where is it? Put it our downloads, File Explorer, downloads, right here. That's pretty small. It's 84 megabytes. So the smallest Dino V2 is 84 megabytes, which means it's comfortably fit on the 2 gigabytes. Maybe not, because sometimes the size of the saved model is smaller than the actual model when you load the whole thing into memory. But okay, keep going. Success of foundation models contributed to the advent and refinement of generative adversarial networks and variational autoencoders. These are other model architectures for generative image generation, which have emerged as the leading approaches for creating high-quality images. Recently, diffusion-based generative models that rely on the process of reverse diffusion to reconstruct images from noise have gained prominence. Yeah, and even this is not necessarily true, right? We've seen a couple different papers now where GANs are making a comeback, VAEs are making a comeback, so it's not entirely clear that diffusion models are going to be the way to do image generation in the future. They might actually fall out of practice, especially since they require many iterations, many inference steps to get the result. One such model is Stable Diffusion that has attracted people's attention for its ability to generate photorealistic images and its flexibility to support various tasks, including editing, inpainting, text image generation, blah, blah, blah. A crucial consideration for incorporating large diffusion models into any application is the choice of where the models will be executed, right? So you can do it on device, or sometimes people call this on the edge, right? The edge as in like the edge of the computational surface, maybe is one way to describe it, right? If you think about, you have the server, you have all these different computers that are standing in between you as the user of a product and the software that is required to run that product. Right on the edge of that is your cell phone, right? So sometimes people call it edge compute. On device is another way to call it that. And yeah, the advantage of that is you don't have to pay for server inference. You have improved scalability because you don't have to scale your product. You can just rely on the fact that people paid for a cell phone and then they're using the compute of their own cell phone. Offline functionality, you don't need. Is that the reason why Apple has a neural engine for its products? Yeah, it's basically that. I assume that Apple is basically trying to do their strategy is all can be on device, which makes sense, right? Because Apple, as far as I understand, they have no data centers, right? Like Google and Microsoft and I think Meta too, all of them have data centers. They've spent years and years and years like buying real estate and then putting in server racks and then getting all the like storage there and like setting up these cloud infrastructures. But Apple hasn't done that at all, right? So they're kind of caught with their pants down. They don't have an ability to serve models from a server. So instead what they're going to do is they're probably going to do on-device stuff. So they're going to create models that load onto your little iPhone, and then you run them on your iPhone locally. And I think it's on brand for them as well, because then they can kind of argue about the privacy thing. right? They can say, oh, the reason we don't perform models inference on our servers is so that your data never has to leave your device, and thus you have better privacy. So I can totally see that. But, you know, then the negative side of that is that on-device presents difficulties due to restricted computational memory resources, right? I think that Google and Microsoft, right? You're never gonna really fit ChatGPT on a phone. I know people have taken the Llama 7B, so Llama CP, this one here. So someone took this Llama model, which was leaked from Facebook, and then they made it. They rewrote it in C++, which makes it faster, and then they also changed the precision so it's even smaller. So 4-bit integer quantization, right? You see here. So they changed it from float 32 to float 16, and then all the way down to 4-bit integer. And then they're able to fit it inside a tiny little, I think 7B is the 7 billion version, 7 billion parameter version. I think they fit it on an actual, here an N1 Pro MacBook, but also I've heard of it fitting on a cell phone. I don't know if that's actually true or if that's just, yeah, here you go, look at this. The 7 billion model, the original size is 13 gigabytes, but they're, with quantization and all these special tricks, this guy here, whoever this is, G.G. Garanov, who is this guy? Grigory Garanov. He works at ViewRay. Okay, we'll give him a little follow here. Usually when you see this sponsor button here, it means that it's someone who's involved in the open source community. This guy from Bulgaria. But scroll down back to where we were. Yeah, they can fit it in 3.9 gigabytes. So it's right on the edge, right? So ChatGPT was telling us that modern cell phones have about 2 gigabytes of memory. I think that's in 2021. I'm sure the, what's the latest iPhone? Latest iPhone. iPhone 14 Pro Max. iPhone 14 Pro Max GPU memory. Technical specs. So this is the hard drive space. This is not the memory. I want the memory. RAM. Don't tell you? Come on. I feel like that needs to be a spec. 3 apps, built-in OS, power and battery, location, cellular and wireless, camera, chip, display, 16 core, A16, memory available in A16 neural chip. Ooh, okay, there you go. So the system Apple A16 chip, which is what's in the iPhone 14 Pro, has 50% more memory. Where is it? Where is it? It's somewhere in this paragraph. Let's search for gigabytes. GB, there we go. Boom. 6 gigabytes of memory. So the Apple chip on the latest phone can hold up to 6 gigabytes. And if we go into the Llama CPP here, we see that 6 gigabytes is not quite enough to fit the 13 billion parameter Llama model, but it's more than enough to fit the 7 billion parameter Llama model. So maybe the 7 billion Llama is nowhere near as good as ChatGPT though. Even the big one, even the 65 billion parameter Llama is still not as good as GPT. So all right, let's keep going here. In the absence of meticulous design and implementation, running these models on device can lead to increased latency stemming from the iterative denoising process, right? Perform inference a bunch of times. Although several successful endeavors have been made to deploy Stable Diffusion to on-device, these efforts are often limited to specific devices or chipsets. Yeah, usually these demos are only on weird, like super expensive phones that have huge chips on them. In this paper, we introduced the implementation for large diffusion models achieving state-of-the-art inference latency compared of Stable Diffusion on our devices. So Samsung S23 Ultra. How much does a Samsung S23 Ultra have? Samsung S23 Ultra CPU RAM. Full phone specs. So let's scroll in here. Main camera, comms, features, test. This is not the. This is just the memory in like a hard drive memory, but I want the actual chip. Where's the chip? Maybe this one. This is the like CPU chip, though. I want the. There we go. Adreno 740. So Adreno 740 memory. So the Qualcomm Adreno 740. Where is the memory? Cache memory, 1 megabyte. That doesn't seem right. Memory type. GPU base, GPU name. I don't even tell you. The Adreno 740 is the fastest graphics chip for smartphones, but that's clock speed, right? So clock speed isn't really super important for, here we go, 12 gigabytes. So that's actually pretty big. So these Samsungs, right, we were looking at the Apple, they have about 6 gigabytes of memory, but this Qualcomm Adreno 740, which is inside the Samsung phone, has 12 gigabytes of memory, which is actually a lot. That's enough to comfortably fit the 13 billion parameter Llama model. So, okay, Samsung has better chips than Apple, and it's the total amount of memory isn't necessarily indicative of the performance, right? The speed of the chip matters, and all the like stuff around the chip, right, also matters, but usually it's a pretty good proxy for the quality of the chip, right? If you have an NVIDIA GPU that has 20 gigs of RAM versus an NVIDIA GPU that has like 10 gigs of RAM, generally the 20 gigs of RAM one is going to be better. It's going to be a later generation. It's going to be newer. It's going to be faster. So memory isn't everything, but it's a good proxy. GANs consist of 2 neural networks. I don't know why they're describing GANs here. You have the generator and the discriminator, and they compete with each other to generate realistic images. GANs are hard to train, which is kind of standard knowledge at this point, but they perform inference in one step, which is why people like them. Denoising diffusion probabilistic models. Okay, this is a type of diffusion model here. Generate high quality through iterative noise removal steps, and Stable Diffusion kind of came out of that. On-device model inference and acceleration has gained increasing attention as it offers several advantages over traditional server-based approaches, including reduced latency. Right? The latency there refers to the fact that you don't have to wait for the stuff to go. So if you're using a server, right, you have to wait for the amount of time it takes for your command to go all the way to the server, and then it gets executed in the server, and then it has to come all the way back to your cell phone. So if you're somewhere that has bad internet, like, that latency can be very slow. So being able to run something locally makes it faster. Softmax operation, common in deep learning, has prompted optimization efforts due to its complexity. So Softmax is a activation function, but it's also used in a variety of different parts of the model architecture. So we've looked at the Softmax here before, but it's basically this curve here. So the point of a softmax is that the input here is usually on the x-axis, and then the output is on the y. So the softmax is a function that takes an input and then transforms it into a certain output. So usually you use this to kind of squash a number between two numbers, right? So let's say here, in this example, they have a softmax that goes from, for example, here, 0 to 1. So you give the softmax function a number, and it'll take this number, and it'll give you back a new number. And that new number that it gives you is guaranteed to be between 0 and 1. And one way that I kind of always understood the softmax, and I feel like makes sense to me, is the softmax and the Gaussian bell curve. So if you look at the softmax, it kind of looks like the total area under a Gaussian bell curve, right? So if you were to go from left to right here across a Gaussian and then incrementally be like add more and more and more, you would see that it kind of almost looks like the softmax. And it's not quite that, but it's kind of a way to think about it in my head that makes it make more sense. But yeah, the softmax is kind of unnecessarily complicated sometimes. Having to calculate that usually requires higher precision data types. So people have been trying to optimization efforts due to its complexity, leading to various acceleration approaches. Okay, so here's some of the different techniques that people have done. Winograd convolution is a special type of convolution that reduces the number of multiplications. Okay. And the transformer architecture has been quite effective and popular, but the transformer architecture is very memory heavy because it's quadratic depending on the size of the sequence. Reformer uses sparse approximation, low rank mixtures, flash attentions, a lot of different tricks that people have come up with to try to reduce the memory footprint of transformers and the computational complexity of the model architecture such that you can run it on a edge device. All right, GPU aware optimizations. So optimizations that are aware of the GPU that you're running it on, right? Different GPUs are going to be able to do different things better than others. So being able to optimize your model architecture and your inference pipelines such that they benefit and leverage all the different features of a specific GPU is important. While the following description is discussing our proposed optimizations for the specific architecture of Stable Diffusion, those optimizations will readily apply to other large diffusion models. Yeah, but how many other large diffusion models are there, right? Like, I could also say that over-optimizing for a diffusion model isn't necessarily the smartest thing to do, especially if we're not entirely sure that diffusion models are going to become the go-to architecture. When performing inference, the prompt involves guiding the reverse diffusion process using additional conditioning based on the desired textual description. Specifically, the main components include the text embedder, the noise generation, the denoising neural network, and the image decoder. Okay. So these are all different parts of the Stable Diffusion pipeline. Let's actually pull them up here. Stable Diffusion pipeline or model architecture diagram. Yeah, let's do this. Show me this one. Open image in new tab. Okay, so what are all the different parts of Stable Diffusion? So Stable Diffusion starts with you typing in a text prompt, right? Such as a person surfing a wave, and you want this image to be generated. So first thing that needs to happen is you need to take this text and you need to tokenize it, right? Tokenizing it is turning it into a sequence of little embedding vectors. We've seen a million different ways of doing this. You could do this with a Hugging Face BERT tokenizer. Like, there's a bajillion different tokenizers. They're probably going to pick one that's very small. Then you feed that into Clip, and Clip will take that tokenized text and turn it into a text embedding, right? And the text embedding is just another kind of embedding vector, right? Just a little vector of numbers that represents the semantic meaning of your text. Then you take a latent seed, right? So Stable Diffusion performs the image or the noise adding and removing on top of a latent space. So it's not doing the noise removal and the noise adding on the actual image in the actual pixel space. It's doing it in a latent space because it's smaller, right? The smaller latent space is 64 by 64, much cheaper and much easier to remove the noise out of a 64 by 64 latent space than it is to remove the noise out of a 512 by 512 image. So first you start with basically just noise, like kind of the white noise that you would see on like a old computer, right? Like a not an old computer, but like an old TV. It starts with just noise, and it's going to say, okay, remove noise, iteratively remove noise from this latent such that you eventually get a person surfing a wave, right? So this is the actual model that removes the noise, right? So it takes in the text embeddings, which are going through this whole pipeline here. It takes in the latent, and it says, okay, I removed one step of noise. And then you're like, okay, all right, send it back, and then say, okay, remove another step of noise, remove more noise, remove more noise, remove more noise. And you're doing that a total of 20 times. So you remove noise 20 times, and then eventually you get a little latent vector that should be the latent image for the real image that you want. So then you take this latent image, you feed it through this variational autoencoder, this decoder part, right? And the decoder takes that embedding and turns it into an image. So the same way that here you can think of this part here as an embedder or an encoder, in that it takes your text and it encodes it into an embedding, right? But here you have a decoder which takes an embedding and decodes it into an image. So Stable Diffusion isn't just one model. It's a bunch of different little parts, right? Usually when people talk about Stable Diffusion, they're referring to this the model here, the UNet here. This is the one that got trained by Stability AI, right? And these are usually not trained with the diffusion model. So this decoder here, this image decoder, is generally some kind of generic image decoder. Maybe, for example, Dino V2 would be a potential image encoder and decoder that you could use. The tokenizer is also some kind of generic encoder, text tokenizer. And then clip is a image and text encoder or embedder. So these models right here, the text tokenizer, the clip model, and the VAE decoder, these are not Stable Diffusion trained, but they're part of the Stable Diffusion pipeline. Okay, so we have our text embedder, which is the clip model, right? That's this part right here, the clip model. Here they show two different parts. They show the tokenizer and the clip, but sometimes in these diagrams, they just get rid of the tokenizer and just kind of say the clip model, it's like kind of includes the tokenizer, but that's not, you can have a separate tokenizer. To encode the text prompt Y. So there's the text prompt, resulting in a high-dimensional embedding vector, the embedding vector of the text, which is here, the text embeddings. This embedding is employed as input to the denoising neural network. The denoising neural network is this part here, this UNet, which is the actual Stable Diffusion model. Furnishing conditional guidance. So conditional guidance here, what that means is that this diffusion model here, this UNet, is conditionally removing the noise. It's not just removing the noise, it's removing the noise conditioned on these text embeddings. Noise generation supplies the random noise in the latent space, which functions as the initiation point. So that's just this. At some point, you have to start with some random noise vector. So that's what they're calling here. The noise generation is whatever generates this. The denoising neural network is this UNet here. Right, so here we go. The network is designed to approximate conditional distributions of the form P of Z given Y, utilizing conditional distributions of the form P of Z given Y. So that little bar in the middle there, what it means is conditioned on Y. So the probability distribution of Z conditioned on Y. So Z is the latent, and Y is the text embedding. So Z conditioned on Y. utilizing a conditional denoising autoencoder, right? So y is the raw text, tau theta y is the embedding, and then your denoising autoencoder, which is epsilon theta, uses z of t, which is the latent image, t, which is the time step, and then tau theta of y, which is the embedded text. And there's going to be a total of 20 iterations here, but you can have 1 step of denoising, you could have 10 steps of denoising, you could have 100 steps of denoising. So generally, the more denoising steps, the higher quality the image that generates is going to be. Okay, the cross-attention mechanism is adopted to operate on the latent space in the text embedding vector, predicting a denoised version of the input during the iterative process. It's iterative in that you're going to repeat this noise removal step a bunch of times. And then finally, once you have your little latent image that has a bunch of noise removed, you need to basically now turn it into a actual image, right? So all you have right now is you have a latent image, which here they're doing a capital E, capital epsilon of X. And you see how the dimensionality of the latent image is much smaller, right, than the dimensionality of the real image, right? So the dimensionality of the latent image is lowercase h by lowercase w by lowercase c, right, which is 64 by 64 and probably by 1. So 64 by 64 by 1 compared to the actual RGB image, right, the actual final image is capital H by capital W by 3, and that's going to be 512 by 512 by 3, which is a much bigger thing. So that's why people do this denoising in the latent space. And yeah, the model that takes you from this latent space into the actual image space is called the decoder. Image decoder. We introduced a set of optimization techniques aimed at enhancing the performance of running the diffusion-based model. All right, specialized kernels, group norm, and GELU. So group normalization is a technique for normalizing the inputs to specific layers for a batch inside a neural network architecture. So normalization layer group, there's the picture in so this is a picture from the layer norm paper, or maybe it's the group norm paper, I don't specifically remember, but basically layer normalization, batch normalization, instance normalization, and group normalization are all kind of the same thing, right? What you're doing is you're taking a bunch of things that are going to have values that are potentially very big or potentially very small, and then you're normalizing them. And what normalization means is that you're saying, okay, well, I'm going to take the biggest of the big things and the smallest of the small things, and I'm going to squash that such that they all lie within some -1 to 1 or 0 to 1, or basically just flatten them out, make them nice and pretty and well shaped, right? And depending on which group of things you choose to normalize, you're going to call it different things. So batch norm, you're going to normalize all of the things in the batch in one batch of training, right? Layer norm, you're going to normalize all the things in one specific layer of the neural net. And I forget exactly what group norm is, but it's like basically some combination of that, right? See here, it's like half of the channels and then all of the height and width, but not everything in the batch. So some kind of special normalization there. This normalization technique works by dividing the channels of a feature map into smaller groups and normalizing each group independently. So channels of the feature map is basically the dimensionality here. So you see C here, the latent space is going to have some number of channels, and that's going to be the dimensionality of the feature map. And this normalization is being applied at groups of channels. So you see here the channel dimension C. We're not doing in layer normalization, you do all the channels, you normalize all the channels, for all the image, right? H and W is the image. But in group norm, you're only not normalizing a subset of the channel. Making group norm less dependent on the batch size and more suitable for a wide range of batch sizes and neural network architectures. Okay, so they're saying here that because group norm, you don't have to do the entire batch at once. You're not as dependent on the batch size, and I guess that makes it faster or easier, or I'm not sure. Each feature value xi, so x here is the RGB image. Why did they choose X if they have X here as the RGB image? So XI is here, they're saying feature value, which is the individual value of a specific feature, but they're also using the word or the variable X to represent the final RGB image. So a little bit of confusion there. Okay. The group mean, mu g, and the variance, sigma g. So mean and variance are going to be the mean and variance of the group in your group normalization. So you take all these values, you figure out what the mean of those values is, basically the average, and then you figure out what the standard deviation of those. And each value, you're going to subtract the mean. So here you take the value of the feature, you subtract the mean, and you divide by the standard deviation. And what that's going to do is it's going to basically take your data and shape it such that it's nice and centered on 0. It hopefully should form a Gaussian centered on 0. I don't have a picture of a Gaussian centered on 0. Okay. Rather than executing the aforementioned operations, which involve reshape, mean, variance, and normalize, sequentially, we devise a unique kernel in the form of a GPU shader that executes all of them in a single GPU command without any intermediate tensors. So this is what model optimization is all about. So when you design a model, right, and you design it from kind of like the top down, you're writing these math equations, and you're like, okay, well, I have all these inputs that are coming in. I want to make sure that they're normalized and they're nice and pretty. So I'm going to normalize them with this specific group norm. And in order to do that, first thing I need to do is calculate the mean of all these, right? Then I need to calculate the standard deviation for all of these. Then I need to take all of them and subtract the mean. And then I need to take all of them and divide by the standard deviation. So you did 4 different things there, right? And if you were trying to run that on the actual, or on a computer, you would basically say, okay, let me do the first thing. Let me take the mean of all of them. Okay, well, I'm going to send all this information to the GPU. It's going to calculate the mean, and then I'm going to get the answer back, right? And what they're calling the intermediate tensor. And then I'm going to take this intermediate tensor. I'm going to say, okay, I want to take all of those, and I want to subtract the mean from them. Okay, let me do one subtraction, and then come back. And then I need to take the standard deviation. Okay, so I want to put it back on the GPU, take the standard deviation, and then bring it back, right? So you're doing all this like back and forth and back and forth. You're basically solving the same thing in 4 lines rather than 1 line, right? And what they're saying here is that, like, hey, they actually understand the kernel, right? The kernel is like, it's the actual thing that's running on the GPU. And they said, hey, rather than doing these 4 kernels in a row, you can actually make one kernel that does all 4 things, and then you don't need to do all 4 things in a row. You don't need to have these intermediate tensors anymore. You just have the entire operation gets done in one. Okay. So that's, and that same idea, that same kind of idea of like, hey, let's do these 4 operations in 1 step rather than 4 steps. That's what these type of people think about all day, right? And the example here is a pretty simple one of like, hey, rather than doing a mean and a reshape and then a normalize in 4 steps, let's do it all in 1 step. There's way more complicated versions of that, which I'm pretty sure is what this paper is all about, right? What they're going to figure out is that, like, hey, you can actually, so we're going to sneak peek ahead here, but here they have a softmax implementation. So softmax is that function we were looking at. And you see how normally when you do a softmax, you have to do a matrix multiply, then you have to do a softmax, and then you have to do another matrix multiply. So this is the keys and the queries. This is like an attention mechanism, right? An attention block. This is kind of the fundamental piece of a transformer. And they said, hey, wait a second, this softmax here and this matrix multiply here, we can actually do those at the same time. So rather than doing one matrix multiply, then one softmax, then another matrix multiply, we're going to do a matrix multiply, and then we're going to do this thing here, which they call the matmul fused softmax. So now, rather than your GPU having to do 3 separate things, it now only has to do 2 things. Okay. So we're going here. The Gaussian error linear unit serves as a prevalent activation function in the model. So a GALU is activation function, which other activation functions include ReLUs and leaky ReLUs and things like that. GALU is a little bit more complicated than a ReLU, right? ReLU versus GALU. I think you guys have definitely seen this if you've watched videos before, but ReLU is very simple, right? It's flat and then it's flat. It's like flat and then linear, versus a GALU has like this kind of like weird like dip, and it has a curvature, so it makes it more annoying to calculate, right? Like look at the equation for a GALU, right? That's so much more annoying than just a ReLU, which would just be a piecewise linear, which is significantly easier to calculate. And here they're saying that the GALU contains numerous numerical computations, and they implemented a dedicated shader to consolidate these numerical computations in a single draw call. Okay. So you're kind of seeing a theme here, right? In this paper, how are they taking a stable diffusion model and then making it run faster, right? So what they're doing is they're basically going through this diffusion model and they're saying, what are all the different parts of this diffusion model? And then can we take all the different calculations that we need to do for this diffusion model, and can we combine them? Where are there opportunities to combine these ops, right, into single ops? Enhancing attention module efficiency. The text image transformer within Stable Diffusion facilitates modeling the conditional distribution. So this is the latent, this is the conditional distribution. This is the latent here, right? Z is the latent, and then tau theta y is the embedded text, which is crucial for the text-to-image generation task. Nonetheless, the self-cross-attention mechanism encounters difficulties with long sequence owing to their quadratic time and memory complexity. So transformers multiply the entire sequence by the entire sequence, right? That's the whole point of attention, is that everything in the sequence pays attention to everything else in the sequence. So the bigger you make the sequence, the size of the square increases, right? That's what the quadratic complexity refers to. We introduced 2 possible optimizations designed to alleviate these computational bottlenecks. Partially fused softmax. So fused here refers to the fact that they took 3 operations and then they fused the softmax and this matmul here such that it's fused into one operation. And this isn't like a great analogy, but like let me do this, right? Some of you that understand programming a little bit better are going to cringe at this analogy, but I feel like it's going to make sense, right? Like think of it this way. If you have a non-fused, right, you have x equals softmax of x, then you have x equals matmul of x, and then you have x equals matmul, softmax, matmul. Fused. That's basically what's happening, right? Is that rather than doing 3 steps, you're doing 2 steps, right? So obviously this doesn't make any sense. This isn't Python code, this isn't pseudocode, and like even if this was Python code, this wouldn't be faster. But that's what they're doing, right? Is they're basically reducing the number of operations. Okay, so what is this partially fused softmax? So here they're going to talk about what exactly the partially fused softmax is, and it's going to be some like little specific thing where they're like, hey, it actually turns out here that you're actually doing it so that we don't need to do X, right? So this is the attention mechanism. So transformers have what's called attention blocks. Attention blocks take in 3 different things here. They take keys, queries, and values. So you have your queries, this little looking E thing here, and this R. What this means is the dimensionality of this query matrix is n by d. And the dimensionality of your keys and your values is m by d, right? Typically, n, m are much larger than d. And once you calculate this, then you need to take the softmax of that. So you see how this is one matrix multiply right here, right? Q times KT, that's the first matrix multiply. You need to do Q times KT. KT is the transpose of T, right? If you want to multiply 2 matrices, you take the transpose of one of them. So that's where your first matrix multiply comes in, is that you need to calculate this right here. And then you need to do a softmax, right? So, okay, well, you have your matrix multiply, you multiply them, then you need to do the softmax of that, and then you need to multiply by the V again here, right? You see? So you have one matrix multiply up here, then you have a softmax, and then you have another matrix multiply there. So you have matrix multiply, softmax, matrix multiply. And what they're saying is that you can actually reduce this. So how do they reduce this? The softmax operation can be performed on the matrix A, and then can be partitioned into 2 steps. Reducing and then element-wise. The reduction operation refers to the calculation of the maximum values in each row in A and its modified exponential sum S as in equation 4. Okay, so L is the partial answer here. So L is like some intermediate version or intermediate matrix that you can get from this matrix here. Specifically, what they're doing is exactly what they said here, the max of each row. Okay. And then the element-wise employed to normalize the values in A utilizing the vector L. So L is the maximum of the max J in each row, and then S is the sum over J of the exponentials of AJ minus max AIK, which has a dimensionality of n. In order to avoid executing the whole softmax calculation on the large matrix A, we implemented a GPU shader for the reduction operations to compute the L and S vectors, resulting in a tensor of size n by 2. The element-wise softmax computation is then fused with the following matrix multiplication involving the matrix V. This approach substantially reduces the memory footprint and the overall of the intermediate tensors and the overall latency. So, okay. So I'm just going to be honest here. I don't know what the fuck this is, right? I don't know enough about like GPU math to know why this exact operation here is faster than this one, right? But there's people at Google and at Meta and at NVIDIA that are very good, and they understand exactly how things are loaded into GPU memory, and not just the GPU memory, but like the different parts of the GPU memory, right? You have different caches within a GPU memory that are further and closer away from the actual computer memory. And they looked at this and they thought about it very hard, and they said, okay, well, actually, if ultimately all you want is this softmax of Q times K over square root of D times V, if you actually do it this way, you can actually do it faster or in less steps, right? And that's what this little paragraph here is. So me as like a more of a machine learning kind of mathy person, like I understand why you do this, right? I understand the attention mechanism, but I don't understand this. I don't understand why taking the maximum of a specific row inside your whatever S matrix and then adding that and then taking the exponent is faster than just doing it this way, but it is. And you just got to trust these people that came up with that particular solution. It is crucial to highlight that the parallelism of computation mapping from A to L S is limited, as the number of elements in the resulting tensors is considerably smaller than those in the input tensor A. To enhance parallelism and further decrease latency, we partition the reduction operation into multiple stages by grouping the elements in A into blocks. Calculations are performed on each block, which are then reduced into the final result. By employing meticulously designed threading and memory cache management, this multi-stage implementation can be finished with a single GPU command and leads to additional latency reduction. Okay, so not only are they fusing these operations, but they're being clever here, and they're saying, okay, that these intermediate results, there's actually, we know that because N and M, right, the dimensionality of these tensors, they're bigger in some dimensions than they are in other dimensions, we can actually be even more clever and make sure that the memory caches and the threading is multiple CPUs kind of working in parallel. We can design that in such a way that we have the fastest possible way to do that. And the reason this is important is because a transformer is literally just hundreds of these things, right? A transformer is just lots and lots of attention blocks all stacked on each other and then in parallel, right? So you have like a multi-headed attention, you have lots of different attention heads, and then you have lots of those attention blocks stacked. So you have attention blocks in the width dimension, and you also have attention blocks in the depth dimension. So if you can figure out how to make that attention computation as fast as possible, and you can figure out these little tricks to make it faster on a GPU, then the entire network is going to be just faster. And this is step one, right? Step one is basically, hey, what can we do with the existing GPU to make attention faster? Step two, which is where the TPU v5 comes in, is, okay, rather than just, hey, we have a GPU, how do we make the individual operations on that GPU more optimal for an attention mechanism? What they did with the TPU v5 is like, hey, how do we design a GPU such that it's actually better at this exact operation, this attention operation? And that's what a TPU is. It's a GPU that has been designed from the ground up for the purpose of being as fast and as efficient as possible for these attention blocks. Okay, flash attention. There are many approximate attention methods that attempt to improve the attention module latency by sacrificing model quality or reduced computational complexity. Okay, so approximate attention methods. So the technique that they described here is not approximate. It's actually calculating everything you need to calculate. But they're saying that if you're willing to kind of have an approximate solution where you're not actually getting the result of softmax qk transpose over square root of d times v, you don't actually get this result, but you get something that's kind of close to it, then you can get even more improvement in memory and latency. And I guess flash attention is that. Flash attention is an IO-aware exact attention. Okay, so maybe not. Flash attention is exact. That utilizes tiling to minimize memory reads and writes, minimizing memory reads and writes between high bandwidth memory and on-chip SRAM. So this is what I was referring to here, that even within the GPU memory, there's different levels there, right? So you have the RAM that's in your computer, right? That's just your standard RAM that your CPU has access to. Then you have the GPU memory, and then within that GPU memory, you have what they're calling here GPU high bandwidth memory, and then SRAM, which is like RAM that's specifically on that GPU. So there's levels of memory available on a GPU. This approach results in fewer HBM accesses than standard attention, making it optimal for a range of SRAM sizes and improving overall efficiency. Although flash attention seeks to enhance latency and reduce global memory read and write, its kernel is highly register intensive, so memory registers. we selectively employ this technique for attention matrices with dimension D equals 40 on Adreno and Apple GPUs. So Adrenos, that's what we were looking at, right? The Adreno is the GPU that's inside the Samsung phone. Next stream suggestion, implement this paper. No way, dude. Like, you can't even implement this. That's the unfortunate reality, is that, like, these people are like real serious, you know what I'm saying? Like, these guys don't fuck around. Like, no, being able to do this kind of stuff, like CUDA kernel optimization and like GPU memory design, like, that's a whole different beast, right? Like, now that's almost more like an old school kind of skill set, right? Like, I'm just a Python guy. Like, I just write Python. I live in like the high level programming world. Like, this type of shit right here, like memory registers and like knowing the difference between HBM RAM and SRAM and RAM, and like loading and unloading things, like specifically reducing the total amount of global memory reads and writes, like, that's a dark art. Like, this is hardcore dark art shit right here. So, I don't know. I'm just lucky that I don't have to deal with this, right? It's the same way that when you have a computer and you look at that motherboard, I can't tell you anything about that motherboard. I can't look at that motherboard and say, oh, right here is your SRAM and this is connected over here to this thing. Like, you know, which is kind of a miracle of human technology that we can do that, right? Is that you can be an expert in something and have no idea how that something is done, right? Because the person that, for example, knows this, right? Like, these people that know about memories and chips and like the exact different types of chips inside a GPU, they probably couldn't tell you anything about how to mine silicon, right? Like, there's people out there that know how to mine silicon out of the ground. They know how to like go into an area and be like, yep, you see this thing over here? That's silicon dioxide or whatever the fuck. And if you take that and you melt it, then you'll get silicon, and then you can use that silicon to make chips. Right? So like, technology is the accumulation of a bunch of people that have expertise in only their specific thing, right? So you have like the people who know how to mine silicon, you have the people who know how to refine silicon, you have the people who know how to design chips, you have the people who know how to design GPUs, you have the people who know how to write the software for GPUs, you have people who know how to write the machine learning software, and then you have people who know how to do the math and the theory for designing the math that ends up being the software that runs on the GPU. So there's layers and layers of expertise there. And you kind of have to trust the people underneath you to do the best of their ability, and you have to trust the people above you to do the best of their ability. Okay, we're getting distracted here. So benchmark results for different devices with each optimization enabled. The numbers in the latency column are in milliseconds, and the numbers in the tensor and weight columns are in megabytes. So these are total amounts of megabytes. What do they mean by weight? Memory usage at runtime. So I guess you're spending... Okay, I think I see what's going on here. The tensor is the actual like input, right? The image, the input to the network. And then the weights are the actual parameters of the model. So you're spending 1640 megabytes to hold the weight, the whole model, and you're spending 105 megabytes just to hold the latent vectors and the images, basically the latent image. And the latency here is in milliseconds. So you have your Samsung S23, you have your iPhone 14 Pro Max, you have the baseline, and then you have with the optimized softmax. So the optimized softmax is this thing here where they fuse the two softmax and the matmul here so they can get the fused operation. And you can see there that with the fused operation, they basically get a 10% improvement, right? And you're just improving the speed. You're not actually, like, the total amount of memory is still the same, but you're just improving the speed or the latency. If you use this SGN GALU, which is like the fancy GALU they did here, right? where they have the GELU and they do it in one call. You again improve the latency, but here you're also improving the tensor and the weight, probably because you don't have to store split and multiplication hops. I don't know how exactly that reduces the total amount of memory. That seems a little weird to me, but okay, I guess. It looks like the weight is the same, but it's just this tensor goes down. The flash attention is this technique here that they were describing, where flash attention uses kind of knowledge about the different GPU memories in order to be more efficient there. See how you get an improvement there. And then plus Winograd. I think they described somewhere. Winograd convolution. So another little trick, you get to 525. So the accumulation of all these little tricks gets you from a latency of 1098 to 525, right? And this is in milliseconds, so that's speed. But one thing to notice here is that actually the Winograd explodes the memory. So even though the Winograd makes it much faster, it does make it take more memory. Winograd convolution transforms the convolution operation into a series of matrix multiplications. The key insight is that by carefully choosing the transformation matrices, many of the required multiplications can be reduced, leading to a more efficient computation. It also introduces increased memory consumption and numerical errors, particularly when using larger tile sizes. Yeah, so this is kind of what they're saying here, is that even though it makes it faster, you do get more memory usage. Almost twice as much memory usage, which is kind of like not good at all. The backbone of Stable Diffusion relies on 3x3 convolutional layers. So 3x3 is the size of the convolution kernel. So convolution is taking a little kernel and convolving it across your image. And the size of that little kernel that you're using to convolve, 3x3 is a very popular size. They comprise over 90% of the layers. So the image decoder, which is this part here, the image decoder is 90% of it is 3x3 convolutions. So if they can figure out a way to make these 3x3 convolutions faster, then 90% of that decoder is just 3x3 convs, and they're going to get a huge benefit from that. Led us to select a 4x4 tile size. Okay, so one thing they did is they changed the size of the tile. We strategically applied Winograd based on heuristic rules only where it would produce profitable results further maximized. So you can see here how this is the memory. So actually, if you use an 8x8 tile size, you're going to do 11x the memory, which is like 10 times more memory, which doesn't seem good at all. Right? There's a kind of a sweet spot here where like, hey, you want to increase the speed without necessarily exploding the memory required. So here you're getting a 2x speed improvement with by 2xing the amount of memory required. So maybe that's fine. Column tensor and weight represent the multiple by which the memory for hosting intermediate and tensors and model weights increases. Okay, so we finally get an explanation here. So weight is the model weights itself, so the actual parameters of the model, and then tensor is just the intermediate values. So intermediate values might be the text embeddings, or maybe the latents here, or maybe you have some kind of normalization and you have to keep track of the means and the standard deviations of the normalizations. So the in this chart here, the weight is just going to be the actual model, and then the tensor is going to be the intermediate stuff. To evaluate the improvement, we carried out a set of benchmarks on various devices. We chose the following targets. The Samsung S23 Ultra, which has an Adreno 740, which is a Qualcomm chip, as we just learned. The iPhone 14 Pro Max A16. So based on our Wikipedia results, the Adreno 740 has almost 12 gigs, And then the iPhone 14 Pro Max has 6 gigs. We provide the latency figures for executing UNet on a single iteration with a 512 by 512 image resolution, measured in milliseconds. We document the memory usage generated during runtime for intermediate tensors, which is the tensor column, and then the memory allocated for holding the model weights in the weight column. And there is actually a memory manager, which is going to reduce the total amount of intermediate tensors by reusing the buffers. So there's all these kind of like intermediate memory caches, and I think that's what it's referring to there. Table's first row displays the result that follows the implementation in the public GitHub repository. Utilizing our internal OpenCL kernels without any optimization, rows 2 through 5 sequentially enable each optimization individually. So they're just describing this table here, how they basically added each thing step by step, and you can see the result of each thing. It is evident that latency decreases incrementally as each optimization is activated. Notable overall latency reductions in comparisons to the baseline are observed on both devices. You get about 50% faster on a Samsung and about 30% faster on the iPhone. Okay, cool. In this paper, we present a set of optimizations that collectively attain groundbreaking latency figures for executing large diffusion models on various devices. These improvements expand the model's versatility and enhance the overall user experience across an extensive array of devices. Wow, that's actually a little bit shorter than I anticipated, but maybe one thing we can do here is let's see if this optimized softmax exists in PyTorch, right? So if we go to PyTorch ops, right? These are all the different PyTorch ops that exist. PyTorch ops softmax. We search here for softmax. Actually, let's look for attention. Scaled.product attention. Here you go. Currently 3 supported versions of scaled.product attention. So you see this one here is just actually doing the standard thing here. So let's actually split this so you guys can see. But if you remember, here, they said that the issue with this is that you're doing a matrix multiply, and then you're doing a softmax, and then you're doing another matrix multiply. So you actually see here, they're actually doing all of that. Here's the first matrix multiply, right? And then they're doing the softmax, and then they're doing another matrix multiply right here. So there's matrix multiply, softmax, matrix multiply, which is no good, right? That's what these guys in this paper were saying. Hey, you don't actually need to do that. You can actually do it in a matrix multiply and then this like weird reduced softmax. So actually, if we go here, I wonder if they have this version also implemented. Is it maybe this one, memory efficient attention? So I don't know what this is. This is just some like framework, Xformers, hackable and optimized transformers. So basically someone went through and did kind of a version of this, but for other things. So you can actually see here, look at the things that they're advertising. They're advertising a fused softmax, fused layer norm, fused dropout, fused swigglue. So these are all, this is a fused operation here, right? So here you have 3 operations, and then here you fuse one of the operations. So you can do that with all kinds of different things. So for example, what is a fused dropout? So dropout here. Fused dropout versus just normal dropout. No. Let's do fused scale dot product attention. Why don't they have a dot product attention that is optimized or fused? Each of the fused kernels has specific input. In the event of a fused operation implementation is not available, an error will be raised why the fused implementation cannot be run. Okay, so I mean they're mentioning the things that they mention here, but they don't actually implement it there. Efficient self-attention PyTorch. Let's see if we can find memory efficient PyTorch. Is this one? This one's still the same. Oh, I think I know why this might be the case. So this implementation of Softmax here doesn't have dropout. So you see this dropout? Right? So whenever you're actually doing training, right? If you're actually performing training, you use dropout. So dropout is a technique where you zero out some of the values in an intermediate vector, an intermediate tensor. And by zeroing out some of those values, you basically have a regularization kind of effect, right? Where the neural network learns to not over index on any specific number. It learns to kind of use all the numbers. When you're performing inference, you don't actually do any dropout at all. So maybe the reason that the PyTorch implementation of scaled dot product attention doesn't have this fused operation is because it wants to account for the fact that people might use this for training and they might want to put a dropout in between this softmax here and then the matrix multiply here with the values matrix. But if you know that this part here is not going to be a thing, then, right, you can actually fuse this softmax with the matrix multiply here, which is what they're doing here. PyTorch attention. Multi-head attention. Okay, so this is the multi-head attention. You have mask, key padding, overrides, not fast, native multi-head attention. This is C code. We've gone deep, we've gone into the matrix here. Multi-head attention forward, that's the one. Can I like find the actual implementation of this? Multi-head attention forward PyTorch. I'm kind of just messing around, guys, so if you guys have any specific questions, feel free to ask. Here we go. Here's another one. You have W split. Where's the softmax? Softmax. Yeah, so here's another implementation of it. You see here, the attention output weights are the Q scaled, right? So the same thing here, the Qs times the transpose of Ks, so the keys, the transpose of the keys. Here's your first matrix multiply. Then you have the softmax, right? This softmax here. But then they also have this optional dropout, so similar kind of thing here, where you have this optional dropout. And then you have the second matrix multiply here with the values. So I don't know. Another reason that we might never find this is that Python machine learning framework code is compiled down. So if you remember when we were looking at PyTorch 2.0, right? We were talking about this idea that the first time you run PyTorch code, JAX is actually a better example of this, but JAX, the first time you run it, it builds a computational graph, and then it'll reduce that computational graph. And one of the ways that it reduces is it does these kind of fusings, right? It does these kind of fused ops where it says like, okay, this is the computational graph of the program that you just gave me. Well, I'm going to take it and get rid of some of these nodes and fuse some of these things together and fuse some of these ops and then give you a better computational graph, right? This kind of compilation that happens when you run it. And PyTorch does the same thing. So when you write PyTorch code in Python, that's probably not exactly what's running, right? It's probably running, what it's actually running in terms of CUDA kernels, and actually CUDA code is some like compressed version of that has been kind of compiled in a sense by PyTorch. So yeah. Is there anything else you guys want here? Because running out of steam. Maybe here I can show you guys this. I got chat GPT. I got access to the plugins. How about that? What if we end with that? What if I go into, here are all the different plugins. Got Kayak, Expedia, Zapier, Instacart, Wolfram. Let's see if this, can you use Wolfram Alpha to plot a softmax function? Is it good? I don't know. Let's see. I haven't really tested it out. I don't know what this is. I don't know why there's like a little flashing thing here, and that seems buggy. Oh, look at that. It has LaTeX. Kind of cool. Okay, let me see if it can actually plot, though. I want to see it give me an image. So I guess this is Wolfram code. I didn't know that like Wolfram Alpha had its own like code, but I guess it does. I will now execute this code to generate the plot. Wolfram Alpha. What is with these like little flashing? So this is a softmax in two-dimensional space. It's a two-dimensional softmax. So you can see here it's actually two softmaxes that are kind of like this, diagonally on top of each other. That's kind of weird. I want a 2D softmax, not a 3D softmax. Yeah, it can plot stuff. Well, it's not actually plotting anything. It's plotting, it's using Wolfram Alpha, which is this. And Wolfram Alpha is basically just like a juiced up like calculator, right? Like it can do all kinds of like weird specific math things. I will now execute this code and generate a plot. Hello from Boston. Hello from Hanover, Germany. Hello, people. How's it going? Okay, so it gave us a softmax, but it gave us a 3D softmax, which we don't want. We want to see if we can get it to... There we go. Look at that. That's pretty good. Let's see if it... Is there anything that we can ask it from this paper that's kind of like... I feel like this is like way too specialized. That's not fuck to do. See, can you shift the softmax down such that it is centered on 0? See if we can get it to shift it down. This is kind of ambiguous though, right? Because I could mean centered on 0 here, I can mean centered on 0 here, so like I'm giving it kind of an ambiguous question, and we'll see what it actually does. So I don't know how to actually read Wolfram Alpha code. I don't even know what the fuck this is, but it basically, it seems like it's plotting a softmax 2D, which is this function here. This symbol here is actually used in Go. Go is a programming language, but it's a way of saying this object, whatever type it is now, is this object. But I don't know if that means the same thing in Wolfram Alpha language. So you see all of it, it did a modified softmax, a new function, and it basically took the softmax original function and then subtracted 0.5. Yeah, that's good. How is the softmax related to the bell curve or normal distribution? So this is more of a kind of a high-level question. Softmax function operates on vectors and produces a probability distribution over the elements of the vector. The normal distribution is defined for all real numbers. Both of them use the natural number e, right? That's the magical number. Like, what is that number? What is... Let's see. What other plugins can we use here? Klarna? Never even heard of this. What the fuck is Klarna? Klarna shopping, Klarna Crunchbase. Klarna is an e-commerce and payment solution platform for merchants. It's from Stockholm, Sweden. They got $1 billion. Holy shit. 8.2 million. Ooh, 630 million from the SoftBank Vision Fund. That's no good, dude. SoftBank Vision Fund is like one of the worst VCs. They don't really know what they're doing. They're just kind of like throwing money around. And they recently got 800 mil. What are they burning all this money on? That's a lot of money. People. A couple different people. Technology. Got fiscal note. Shop. Elo Family AI. What the fuck? Family AI. AI Copilot for parents. What? So it's just GPT-4? Like, what the fuck? What is the point of this? It's just GPT-4, but not? Like, what? That seems kind of stupid. Let me see. Let's look up Milo on Crunchbase. Milo AI Crunchbase. Milo AI is from Vancouver, British Columbia. They raised a seed round in 2020, so very long time ago. Works there, Avni Patel. They're a Y Combinator company. And they got invested in by this guy. Probably made his money in YouTube. Part of the Stanford Mafia as well. Okay. Cool. Not quite at 2 hours, but I think we'll end it there. I don't really know what else to talk about. Let me know what you guys want in terms of papers, repos, maybe people. It was a great stream. Hopefully it was helpful, RW. Like, this was a little bit more intense than I thought it was. Like, the paper wasn't actually like very long. It was a very short paper, and like really they didn't do a super great job explaining like why exactly this is better, right? They were just like, oh, here's this like one weird special like trick that we learned in order to instead of have three operations, we fuse these two operations. But I don't know, maybe I'm just being unrealistic, and it's kind of it's gonna impossible for someone to really truly understand what the hell this does, because just GPUs are so complicated now. Like GPU H100, in the H100 diagram, diagram. Yeah, like there's so many different things here, right? So like there's all these different memory registers and caches, and like this, what people are playing with here in these types of operations and these types of optimizations is like they're playing with like just milliseconds and like reducing one little thing like that. So you see here, they're like, oh, okay, well, I know that if I don't move the stuff from this HBM cache and I can move it into this other very large cache here, then I can save an extra step of having to move it over here, right? It's like those kind of like 500 IQ like little like speed optimizations. But even the people who like design this stuff, I feel like wouldn't even be able to fully explain it. L3 cache, L2 cache, L1 cache, and then this is the actual SM, I guess, is what the one that's actually doing the matrix multiplies. Okay, I'll stop pretending to understand this. Hope you guys have a good weekend. And yeah, like and subscribe.